Hi, everyone. In this video, we'll begin the next section in which we'll be discussing the Riemann integral and Riemann-Stieltjes integration. Before we begin, it'll be important that we define some common terminology that will be important as we go about defining the Riemann integral. And to begin, today we want to start with sort of a historical notion of the problem of finding the area under a curve. Now, finding areas and volumes is a problem as old as antiquity itself. But really, we start to see progress being made in the sort of 1600s, 1700s, as mathematicians begin trying to find the areas of certain types of planar regions. While we won't go through a full history of that, you can find in the book a short discussion of the history along with a number of references to sources which speak more about the history of these problems. But fundamentally, if we think about the question of, say, finding the area under this curve between points A and B, so I can imagine sort of restricting myself here and restricting myself here, and trying to find the area directly under this curve. So again, this sort of naturally defines then, another sort of boundary. So trying to find the area enclosed in this region here. Now, in that long history of trying to solve problems of this type, one of the most common ideas of trying to find the area of any irregular sort of shape in the plane, the first idea is always to decompose it into regular shapes that you do know the areas of. So, right, so if I were to just give you, just to sort of imagine, this this sort of figure in the plane, right? You would find the area by first finding the area of this triangle, then finding the area of this semicircle and adding them together. Now, of course, it's not going to be so easy here. If we look at this, right, there's really no way of decomposing this so that every piece of it will be some regular shape that we easily know how to take the area of. So we sort of first relax the problem and say, okay, let me give up on, at least for the time being, on trying to find the exact area. Could I approximate the area arbitrarily well? Okay. So anytime we then think about approximating, the question becomes, well, what do we want to approximate this with, right? There are lots of different shapes in the plane that we easily can find the area of. So, you could say, well, I'm going to take and see how many, circles of radius 1 I can fit within this region of the plane, right? And you could do that, right? You could go around and you could say, okay, I'll put maybe that's a circle of radius 1 there and a circle of radius 1 here. And, maybe you squeeze another one in there, I don't know. And then, maybe you sort of squeeze one in here, but then you're missing some down here. Maybe you could get I don't know, maybe a half circle down here, right? And so you see that right off the bat, even just the question of how am I going to squeeze these circles in here is sort of problematic. They don't fit together well. There's a lot of dead space here, right? I can't really figure out how to cover that. I guess I could maybe try and go back in and take some smaller circles, right, and sort of wedge them in there. But now I've got circles of two different sizes, and then that still leaves some dead space here. Circles fundamentally just don't sort of pack together very well. In fact, circle packing problems are themselves, a whole sort of subgenre of mathematical problems. So circles are probably not the best bet here. So we've recognized from our very brief attempt at circles that we should try something that at least stacks together fairly well. So what about rectangles? And so you saw in a Calculus 2 course, right? In a Calculus 2 course, the idea was probably to take this interval AB, divide it up into n equally spaced sort of rectangles. So let's just, for the sake of not making this too difficult to draw, let's say we just did 3 rectangles, and you would approximate that by taking this as your base, these 3 segments as your base, and then you would determine a height for the rectangle by either taking maybe the function value at the left endpoint, in which case, say you would end up with something that looks like this. So there's one rectangle. Then you would have another rectangle that, say, looked like this. And then you would have one final rectangle that, say, looks something like this. Okay. And then you could calculate the areas of each of these rectangles, right? And add them together, and that would sort of approximate, right? And it's an approximation, right? You're overcounting some area here, you're undercounting some area here, overcounting a little bit here. But maybe in the grand scheme of things, maybe it comes out as sort of a wash. You overcount a little bit, you undercount a little bit. Maybe you end up sort of close. The idea was then, well, if you wanted a better estimate, right, what would you do? You would just take more rectangles, right? So if you took 10 rectangles, now because I'm taking equally spaced rectangles, right, that means that each of their bases is a little bit smaller. Maybe I get a little better approximation. Okay, so that's all well and good. That's a perfectly good way of doing this. And those were the kinds of Riemann sums that you constructed in a Calc 2 course. Now today, we are going to talk about Riemann sums quite a bit, but we're actually going to make our notion of Riemann sum a little more general than what you would have seen in a calculus course. I do want to point out, however, that there is another option. There's no reason we sort of in Calc 2, we put these rectangles in and we all go, okay, yeah, great, that's how you do it. And we draw these rectangles so that they're all sort of taller than they are wide, right? The base is what's getting really narrow. But there's no reason we have to do that, right? You could very reasonably say, why don't we sort of why don't we put our rectangles in this way, right? That's a really easy rectangle to draw, right? And then I could draw another one here, right? And then maybe another one here. Okay. Now you start to realize that as soon as I go sort of one more, there is a slight problem here, which is if I want to estimate the area under this curve, if I draw this next rectangle, then I'm going to have to sort of cut it, right? So I'm maybe going to have to do something like this. So this rectangle here, when I go to find this area, it's sort of like its height, is fine, but its base is really, the length of this interval plus the length of this interval. And of course, this problem occurs here because this function is not invertible, right? This function, excuse me, is not one-to-one. And so we have this problem here. Now, is that really a big problem? Well, for this function, probably not. Maybe algebraically, it might be a little tricky. But it does require some work. And you can, in fact, take this notion of approximation. So you could keep going with this. And you could keep going and build a theory of integration based on this idea of sort of horizontal slices. And it actually turns out that in some appropriate sense, what you would actually end up developing is not the Riemann integral, but something called the Lebesgue integral. Now, if you go on and take 5620, then we will actually talk about the Lebesgue integral. And actually, much of the work becomes how do you figure out the length of this subset of the domain? Now, here it's just two intervals, so it's not too complicated. But actually, for really sort of exotic types of functions, these subsets can be really weird subsets of R. And so thinking about what their length is becomes a little tricky. And that's actually why we end up defining something called the Lebesgue measure. So it helps us sort of measure the base, and then we develop an integral based off of that. So I say all that to say only that it's actually perfectly natural to think about sort of, partitioning your area this way. And if you followed that in a certain logical way, you would actually end up developing just a different type of integral. Now, as it turns out, the Lebesgue integral is actually an extension of the Riemann integral, which is to say that every function which is Riemann integrable is also Lebesgue integrable, and the value of the Riemann and Lebesgue integrals match. There are functions, however, which are not Riemann integrable, but are Lebesgue integrable. So again, it really is an extension, a way of integrating some more functions that we can't necessarily integrate using just the theory of the Riemann integral. But again, that's a bit outside the scope of what we're going to do for now. So for now, we're going to stick with the notion of creating these sorts of vertically oriented rectangles to help us approximate the area. So our goal will be to construct Riemann sums, but before we can do that, we need to define some terminology. So the first thing we're going to need to define is a partition of the interval AB. So a partition of an interval AB is a collection of n plus 1 points. So we'll call that collection of points P. We will call the points the x sub k's. So x0, x1, x2, x3, all the way up to xn. Okay. And we want them to satisfy the property that x0, the first point in your partition, is just A. xn, the last point in your partition, is just B. And the points are ordered. So x0 is less than x1, is less than x2, so on and so on and so on. So if we just think about this visually, we have an interval AB, and we're going to create a partition. So the first point in our partition, x0, will just be our A. Our last point, xn, will be B. And then we will just take these points. There's no requirement here that these be evenly spaced, just that I might take an x1, an x2, an x3, an x4, so on and so on. And maybe just for the sake of this picture here, we'll take a partition with 6 points. So we'll go up to x5. Okay, so this is just a partition of the interval AB. Now, we want to then define a few things related to the partition. The first thing we want to define is the norm of the partition. Now, remember when we were constructing Riemann sums in calculus, I said we often just sort of took evenly spaced points. Now, one advantage of taking evenly spaced points is that you know that as you add more rectangles, you force the size of the base of each one to get smaller. However, here, I can add points to this partition without affecting any of the other bases, right? So I could just come in here and add one more point into my partition, say right here, right? And if I were to add this point into my partition, that hasn't affected any of the other bases over here. So at some point, what I want to be able to do is I want to be able to describe, so I want some measurement of sort of how big the bases of the rectangles are. So how big are the gaps in this partition? So what the norm of the partition does is, first of all, it defines these quantities delta x sub k. Delta x sub k, so delta x sub 1 is just the length of, and actually let me put it up here, is just the length of this first subinterval. Delta x sub 2 is just the length of this second subinterval. So again, delta x sub k is just x sub k minus x sub k minus 1. So it's the kth value in your partition minus the previous value. So it's just giving you the lengths of each of these partitions, right? So this in here would be delta x3. This would be delta x4. And then finally, this would be delta x5, those widths, okay, those distances. Now, the norm of the partition is defined to be the largest of all of these. So like visually, if I'm looking at this, probably the norm of my partition is delta x4. Now, why do I care about the norm of the partition? Instead of saying that I want to take more and more rectangles in my partition, because again, that doesn't guarantee that the bases get small, what I'm going to start doing as we define things about the Riemann integral is I'm going to say I want the norm of my partition to get small. If I say that the norm of my partition is getting small, that means the biggest of the bases is getting small, which means they're all getting small, right? So this norm of the partition, we're actually not going to use it very much today, but it's going to become really important when we write down some of the technical definitions for the Riemann integral. Now, the final thing we want to define is a special type of partition called a tagged partition. Now, a tagged partition is just you take a partition, and then once you have that partition, and let me clean this up a bit. Once you have that partition, you're going to pick a set of tags to go with that partition. Now, the tags are these values CK, where these CKs just live in in the kth subinterval. So again, for example, you have here, say here's x0, which is A, here's B, which is xn, and let's again just imagine you have, say, like 5 or 6 total points. Um, so here's x1, x2, x3, and x4. All right. And now what we're going to do, so this is just a partition. A tagged partition means we come in here and we're going to pick C1 somewhere in this interval from x0 to x1. And it could include x0 or x1. So maybe I'll come and choose C1 here. C2, I need to choose somewhere in here. I could choose it to be the same as x2. C3, I can choose somewhere in here, okay, between x2 and x3. Maybe I choose it there. I could actually choose C2 and C3 to be the same thing if I wanted, right? Because C2 has to be between x1 and x2, including x1 and x2. So C2 could be x2. C3 has to be between x2 and x3, including x2 and x3. So it could also be x2. Okay, but just for visualization here, let's not do that. So I'll choose a C4 somewhere in here, and maybe a C5 there. Okay, so now if I take this partition, these x values, together with this collection of tags, this is what's called a tagged partition. So again, I think in some ways it's helpful to think of it as being a partition together with a set of tags, and that forms a tagged partition. Now, let's see how all of this is going to help us when we get over here. So let's go back to this problem of sort of finding the area. So the whole idea is going to be, I want to approximate the area under this curve. I'm going to take, and the first thing I'm going to do is create a partition. Actually, use this color. So my x0 is going to be A. My B is going to be my, whatever it is. Let's, for the purpose of illustrating this, we'll again just go up to 5. Okay. And then we'll pick some points in between. So maybe there's, x1, x2, x3, and x4. Okay. 1, x4. And again, if my goal is to stack some rectangles in here, now what I have is I have my sort of sides of my rectangles, right? So I know where the sides of those rectangles are going to be. So the partition itself helps create those. Now, what about those tag things? Well, the tag things are going to tell me here in a minute, right, is the tag is going to tell me, so like C1 sits here, okay? This tag is going to tell me where to pick the height of this rectangle, right? So I'm going to use that tag information then to create the height of this rectangle, okay? Wherever this tag C2 sits over here, if it sits right here at x2, then that'll be like here I'm going to do a right-hand rule. I'm going to use, oops, a little low. I'm going to do a right-hand rule. And then the height will be there. And then if my C3 is sitting somewhere here, then I would come up here and I would use my function value here for the height of my rectangle. And again, that's going to be on this whole interval here. Right? Okay. So these tag values are going to tell me sort of how to choose the height of my function. The tag values are giving me the x values that I'm going to plug into my function to get the height out. So each of these pieces are sort of important moving parts in eventually defining our Riemann sum. Okay. So given that we have all these moving parts now, let's actually define that Riemann sum. So suppose we have a function f, which maps from a, b into r, which is bounded. And I want you to imagine that P is a partition with tags CK. So you have partition P together with a set of tags CK. So that forms a tag partition of AB. Then we can define the Riemann sum of F with respect to this tagged partition as the sum from k equals 1 up to n of f of ck times delta xk. So notice here, just from this definition, right, that this is really just giving you the height of the kth rectangle. Okay, and this delta xk, remember, that's just the width of that kth subinterval. So this is really just giving you the base of the kth rectangle. Okay, and so if you take the height of a rectangle times the base of the rectangle, right, what I really end up with here in this term, right, this is just the area of the kth rectangle. And I add them all together, right, to get my approximation. Now, I don't love this notation that the book uses. So we have here that this is the Riemann sum of F with respect to the tagged partition P. And the reason I don't like it as notation is because you have to be very careful here. If you keep your partition the same, but change the tags, you have a different tagged partition. Okay, so if you change just the tags here, you keep the partition the same, but you change the tags, then you are actually changing this P, even though P is often the notation that we use just to reference the partition itself. So we just have to be careful with this notation here to recognize that even if we keep the partition the same, if we change the tags, we're really changing the tagged partition here, and so we're changing this value, and we should expect potentially a different Riemann sum. Now, because of this issue, you will see that in some books, they might actually write this instead as like the Riemann sum of PSF, where this S represents the tags and P represents just the partition. Now, in fairness to the author, there are problems with this notation too. For example, it's impossible here to necessarily just change the partition and not have your tags change, right? Because if you change your partition, your tags may not make sense anymore as tags of that partition. So again, there's no perfect notation here. What I just want us to be aware of in the big picture is you really have two moving parts. You have the partition and you have the tags. And if either of those pieces changes, then you should expect the value of your Riemann sum to change. And that's really the big piece of that. Now, again, just visually to go back to this picture, let's imagine here, right, we're sitting maybe in sort of here's maybe x sub k minus 1. Sitting over here is x sub k, right? And we have a tag value, say, sitting right here at this point of discontinuity. Okay, so let's say right here is c sub k. Okay. Now, notice here again that the approximating rectangle in this region, right, is going to be this, right? So this has height. If I come over here and look at this height, this is going to be f of c sub k right? This base here is delta x sub k, right? And so the area of this one rectangle is f of c sub k times delta x sub k. And again, we do that for each little piece of our partition, and then add them all together. That's how we get the Riemann sum. Now, let me emphasize a couple of things. If you were to perturb this this tag, sorry, I couldn't come up with the word tag. If you were to perturb this tag ever so slightly to the right, right? So you were to move it just a little bit to the right. And let me maybe do that, and I'll sort of put that in yellow. It's hard to tell the difference between the yellow and the green sometimes. But let's say I were to move this over here and make CK star, okay? Notice that that small change in that tag is actually going to correspond to a very large change in your Riemann sum. So your Riemann sum does not necessarily depend continuously on your choice of tags, okay? So you have to be a little bit careful here, right? As you can move tags, nudge them just a little bit one way or the other, can cause actually very large fluctuations in your Riemann sum. That does not mean that this function is not nicely behaved. It doesn't mean that it's not going to be Riemann integrable. In fact, this function would be Riemann integrable. But it does mean that we have to be a little bit careful about some of the assumptions we make. And a lot of this really boils back to, if you look at that definition of Riemann sum, we are defining a Riemann sum not just for a continuous function, but we're actually defining it for a bounded function. So since our function f is not continuous, at least in this case, and we're not necessarily requiring that it be continuous, we shouldn't necessarily expect that our Riemann sum will vary continuously with the values of the tags. Okay, so again, just a little something as we move into some of this Riemann integration stuff. I think it's important to remember that we're not necessarily always thinking about the function itself being continuous. And so we have to be a little bit careful about some of the assumptions we make about how a Riemann sum might behave. Now, to make sure we're making some sense here, let's sort of stop and check in and see if we could calculate a few Riemann sums. So what I want to do here, so let's imagine that my function f, I want to be chi sub q of x. Now, what is that function? So in general, this is actually notation for an indicator function. So if we have a set A, chi sub A of x, so I would normally read this as the indicator function of A. This is defined to be the function that has the value 1 when x is a value in the set A, and 0 if x is a value not in A. Okay. So in particular, if we're looking at the indicator function of the rationals, this is a function which when I plug in a rational number, it gives me out 1. When I plug in an irrational number, it gives me out 0. Okay. So let's think about some Riemann sums of this function. So in order to think about a Riemann sum, I need a function which is bounded. This function is bounded, right? It only spits out 0 and 1. So it's certainly a bounded function, okay? And I need a tagged partition. So I'm giving you here, let P be the partition. So it's a partition of the interval 0, 1. And its values are 0, 1 over 100, 1 over 99, 1 over 98, 1 over 97, 1 over 96, so on and so on and so on until I get to 1 over 3, 1 over 2, 1 over 1, which is just 1, okay? So the first thing to note, that this is in fact a partition, right? These are all increasing, right? It's a partition of 0, 1, because my first point is 0 and my last point is 1. Okay, so I have a partition here. So if I want to calculate a Riemann sum, I need some tags. So what I want to do is I want to calculate the Riemann sum of this function with this partition for several different cases of tags. Okay, so the first case of tags I want to think about is what if c sub k is equal to x sub k minus 1. So recall, right, by definition, our tag c sub k must be in the interval x sub k minus 1 to x sub k. So what am I really saying here? I'm saying choose the c sub k to be the left endpoint. This is like calculating a left-hand rule or a left-hand sum for a Riemann sum that you might have seen in calculus, right? So what if our tags are just the left endpoints of all the intervals? Okay. Well, in general, okay, what is a Riemann sum? So in general, we define a Riemann sum to be the sum k equals 1 to n f of c sub k times delta x sub k. All right, so what's going to happen here? Well, here our ck's are x sub k minus 1. So this is going to be the sum k equals 1 to n f of x sub k minus 1 times delta x sub k. Okay, well, what can we say about this? So this function, right, is an indicator function of the rational. I really just need to know, is this value going to be rational or irrational for each k? Well, these x sub k minus 1, that's going to be x sub 0, x sub 1, x sub 2, all the way up to x sub n minus 1. I'm choosing the left endpoints, so I'll never pick up that last partition value there. But in any event, notice all of these are rational numbers, right? So f of those rational numbers is just going to be 1. So this will, in fact, be the sum k equals 1 to n of 1 times delta x sub k. Or we could just write the sum k equals 1 to n of the delta x sub k. Now, let's think about that for a moment. So what are all of these things? These delta x sub k's, they're the lengths of each of the little subintervals. So like delta x sub 1 would be 1 over 100, the difference between these two values. Delta x sub 2 would be the difference between these two x values. Delta x sub 3 would be the difference between, 1 over 98 and 1 over 99. So on and so on and so on. Okay. Well, what do those all have to add up to? This is a partition of the interval 0, 1. So if I add up the lengths of each of the subintervals, it better add up to the length of the whole interval, right? So if I add up the lengths of all the subintervals, I'm just going to get 1. Okay. And so here I can actually calculate if I do a left-hand sum for this function with this partition, I am going to get 1 as my value for that Riemann sum. Okay. Now, I should point out here, the same thing would work if you chose to do right-hand endpoints, right? If you chose to do c sub k is equal to x sub k, the other thing that would happen is you'd sort of shift the endpoints. The first one would be 1 over 100, then 1 over 99, all the way up to 1, right? The problem here being 0 is never the right-hand endpoint of any subinterval. But each of those would be rational values, so you could follow this through. The only thing that would change is here you would just write x sub k instead of x sub k minus 1. But you would still get that Riemann sum was 1, even though in this case you changed the tagged values. Okay. Now, what if I look down here? So what is this? C sub k, I'm going to choose my tagged values here to be, what is this? This is the average of x sub k minus 1 and x sub k. This is like a midpoint rule, okay? And you can make exactly the same argument for the midpoint rule because the average of two rational numbers is always another rational number, okay? So here we can say since C sub k will always be rational, then here the Riemann sum will also be 1. Again, same argument, right? The C sub k will always be a rational value. Since it's always rational, f of that rational value will always be 1 because of how we've defined our function f. And so by this exact same line of argument here, the value of this ends up being 1. Okay. All right. Now, lest you think every Riemann sum here is going to have the value of 1, what would happen if we chose our CKs and we get to choose them from the closed interval, but this time I'm going to say I'm going to choose my tags so that they're in the open interval x sub k minus 1 to x sub k, and they are not rational. Now, the first question might be, how do you know you can do that? Well, we actually proved in a homework, right, that any uh, open interval contains at least one rational and irrational value. And in fact, as soon as you have at least one, you actually have infinitely many. Okay. So in this open interval, there's always going to be at least one irrational value that I can choose to be my CK. So say I choose my tags that way. Well, if I choose my tags that way, then what's going to happen? So I'm going to have a sum, oops. I'm going to have a sum k equals 1 to n f of ck delta xk. But now all of these ck's are not rational. And since these are not rational, f of an irrational number is 0. So this is sum k equals 1 to n of 0 times delta x sub k. But 0 times that delta x sub k is going to be 0. It's going to be a finite sum of zeros, which is going to be 0. And so here you have a Riemann sum, which is 0. Now, again, none of this is particularly deep, but what is important here is that we really understand what each piece of this notation and this definition is giving to us. And it's going to be important because later on, for example, we're going to be doing things like saying, oh, okay, look, I've factored out a bunch of stuff and I'm left with the sum k equals 1 to n of delta x sub k. Oh, that has to be the length of my interval, right? So a lot of these things are ideas we're going to be coming back to, and we're going to be using in very subtle ways as part of larger proofs. So it's nice to just start by getting a little more comfortable with the notation. All right. Now, there are limits to Riemann sums, and to help us see one of those potential limits, let's come back to our sort of motivating example here. And again, I'm just going to sort of imagine for a second I'm on some subinterval of my partition here, and I'm looking here. Now, if I just forget about Riemann sums for a second, if I just think about like what might be reasonable approximations, right? I might say, you know, I want a rectangle that sort of has this height. Like, I don't think this is an unreasonable approximation of my function. Now, does it overcount some area? Sure, but so it overcounts some area here. It also undercounts some area over here, but hey, you know, nothing's perfect. So, you know, I think that's not a terrible approximation. But what I want to point out is that one of the limits of our Riemann sum is that this could never appear as one of the approximating terms in my Riemann sum. And why not? Well, this value is never a value, this height is never a value that the function achieves, right? Sort of in the limit, you're approaching this value, but because I have an open circle here, my function never actually achieves that value. So if I came here and tried to say, oh yeah, I want my tag value, if I came here and say, I want my tag value C sub k to be right here, well, if your tag value right there was C sub k, f of C sub k is right here, right? So this is f of C sub k. And so you would, if you tried to do a Riemann sum, you would get this as your approximating rectangle. Okay, but again, I feel like I should be allowed to have this as an approximating rectangle. So the question becomes, how would we describe this value then, given that it's not really an output of the function? So we sort of mentioned before, if we look at this, you know, it's sort of a value that our function is approaching. Another way to think about this is to come over and think about it in terms of the range space. Okay, so if I think about the outputs of my function on this interval x sub k minus 1 to x sub k, right, I can sort of see, okay, over here, I get out, this is sort of my minimum value that my function, and I actually get it out, right, of my function right here, okay? And then I get all the values between here up to this f of c sub k. if I come over here, I get out all the values up to here, and I do get out this value. Okay. So I can sort of over here on the y-axis, I'm going to sort of plot the intervals that are in fact in the range of my function over this interval. And if I come up here, right, I also hit some values up here. So I do actually hit this value here. So if I sort of track this all the way across, okay, I do hit this. And then I hit every value sort of right until I get here, and I don't quite hit this value. Right, so maybe this is like sort of open, right? But I hit everything in between. Okay. So one way to think of this value is it's the supremum of the range values of the function over this kth subinterval. Okay. So I could define this height, maybe I'll call it capital M sub k. I could define it to be the supremum over the kth subinterval of my values of my function. So I look at all the values that my function takes on over this interval from x sub k minus 1 to x sub k, and I choose the supremum of all of those values. Now, it's not a maximum, right? Because I don't actually achieve that value, but it is a supremum, okay? It's the least upper bound sitting here, okay? Well, likewise, if I do that, I could also here actually define a lower bound. So I could define a little m sub k, and it could be the infimum over all x in the kth subinterval of my f of x values. Now notice here, this is actually a value that this function does happen to obtain, okay? It obtains it because it's continuous at this point, okay? The discontinuity here causes us not to achieve this maximum value or this supremum value, okay? Now, what we could do is we could actually do this on each subinterval. On each subinterval, I could look at the range of my function. I could calculate the supremum of the range of that function on the subinterval. And I could set that to be the height of a rectangle. And I could do that. I could choose the maximum sort of heights on each subinterval. And I could construct it's not a Riemann sum anymore, right? Because this is not f of ck for any ck, but it is some sort of approximating sum. I could also do this by choosing the infimums, right? So all the rectangles sort of would be below the function, okay? So if I do that, I get something that's like a Riemann sum, but it's not exactly a Riemann sum. And so we give it a different name. And this is an idea that is, or in the resulting sort of integration theory that comes out is named after a mathematician, Darboux. And so instead of calling these Riemann sums, because again, they're not really Riemann sums, we call these sums upper and lower Darboux sums, respectively. Okay. So once I just get this cleaned off here, we'll formally define those upper and lower Darboux sums. And again, they sort of help us recover some things that we can't exactly do with a Riemann sum. So here's the definition. Again, we're going to take f to be a bounded function, and we're going to take a partition. Now notice here, I don't have any tags. One of the advantages of upper and lower Darboux sums, you don't need any tags. It's based purely, the heights of the rectangle are based purely on those definitions by infimums and supremums, and not on being the value of the function at any particular point. So I don't need tags here. So I can define these upper and lower Darboux sums for any bounded function with a given partition of an interval. So if I do that, I set the capital M sub k and the little m sub k, just as I did before. So in each subinterval, I pick the supremum of the function on that subinterval, that'll be the m sub k, and I pick the infimum of the function on that subinterval, that'll be the little m sub k. And once I have those, I can define the upper and lower Darboux sums. The upper sum is just you use the capital M sub k's for the heights of each of your rectangles. And the lower Darboux sum is just you use the little m sub k's. Okay, so you end up with these upper and lower Darboux sums respectively by using these supremum values and infimum values appropriately. All right. So again, graphically, let's just think about what this would be. So let's say we took some particular partition of these things. So we have x0 being our A. Let's say we just have an x1. Maybe I'll make this really basic, an x2. And then let's just say our B is our x3. Okay, so very, very small partition here. And so the idea here is simply on each subinterval, so in this first subinterval, I'm going to come here. Oh, sorry, that should be, say, x sub 1. Yeah. So on this first interval, right, I'm going to come here. Now I'm going to find the supremum and infimum values of my range here. So the infimum would actually be here. So this would be the little m sub 1. The capital M sub 1 would be the supremum of the function over this interval. That would be capital M sub 1. And so if I'm doing an upper Darboux sum, right, I would choose this as my approximating rectangle. If I'm doing a lower Darboux sum, right, I would choose this as my rectangle. Okay. Again, on the second subinterval, I look at the smallest output value. Again, that actually, it looks to be about the same place. Maybe we can just say M2 is equal to M1. Again, they're about the same height there. But the maximum over this subinterval, or sorry, the supremum, is actually up here. And so this would be my capital M sub 2. And so again, I could have an upper sum, which would use this as the rectangle. And I could have a lower sum, which would use this as the rectangle. Okay. And then, of course, I could continue on. I could do this last one, right? So without labeling everything and belaboring this, right, I would get an upper sum that would look something like this. Ooh, very squeaky. And a lower sum that would look something like this. So then the lower Darboux sum would just be the sum of the areas of these three pink triangles, and the upper Darboux sum would be the sums of the areas of these orange triangles, or sorry, orange rectangles. All right. Again, notice no need for a partition here. So these are actually really nice to work with in some ways because you don't have to keep track of a partition. Or sorry, you don't have to keep track of a set of tags. You just need the partition values. The trade-off is the definition of that capital M sub k or little m sub k is a little trickier, right? It's not just f of some value. It's defined as an infimum or a supremum. And so there are trade-offs there. You don't need tags. But it does make the definition of those heights a little bit more difficult to work with. We will see that all of these things have an appropriate place, right? Often what we're doing in this course, and actually really in all of mathematics, is we're adding different tools. None of them necessarily do something that nothing else does, but they might do it in a slightly different way. And so what becomes important later on as we start proving things is, well, which notion or which definition is actually going to be the most helpful to solving the particular problem at hand. Now, the last thing I want to mention before we go back through one more example about upper and lower Darboux sums is if you have a continuous function, then every upper and lower Darboux sum can be realized as a Riemann sum. Why is that? If your function is continuous, then by the extreme value theorem, it actually will achieve its maximum and minimum values on each piece of that subinterval, right? So on each of the little subintervals of the partition, whatever that capital M sub k is, there will be some point in that subinterval where that value is achieved if your function is continuous. However, when you have a function that's just bounded, but not continuous, then you can have upper and lower Darboux sums that are not realized as any particular Riemann sum. All right. Last thing I want to do is just go back through this example again and think about it in terms of upper and lower Darboux sums now. So if we think about the upper and lower Darboux sums, right, the first things we have to figure out are sort of what are the capital M sub k's, right? That's going to be important for the upper Darboux sum. And what are the little m sub k's? So the capital M sub k's are just defined to be the supremum for x in x sub k minus 1 to x sub k of f of x. And now we're again back to this particular function, right, which is the indicator function of the rationals. Well, in each of these intervals, there will be rational and irrational values, which means that your range, right, is really just the set which consists of the number 0 and the number 1. What's the supremum of that set? It's just 1, right? So the capital M sub k's are going to be equal to 1 for every k, right? On every subinterval of your partition, you're essentially what this is saying is on every subinterval of your partition, you're going to have a rational value. That rational value is going to give you out 1, and that's the biggest thing you could ever possibly get out. So the supremum of on each subinterval of your function is just 1. The little m sub k's, similarly, if I look at the infimum over all x in the kth subinterval of my partition, again, this set of output values just consist of the number 0 and the number 1 because this interval contains rational and irrational values. So the infimum of that set, which is just the singleton 0 and the singleton 1, the infimum is just 0. And so I get that each of my little m sub k's for every k value is 0. So what does that tell us about upper and lower sums? Well, that tells us that my upper sum, which is defined to be the sum k equals 1 to n of capital M sub k of delta xk, these are all just 1. So this is again just the sum of the delta xk's, which is just going to be the length of my interval, which is 1. My lower sum, that's just my little mk's times delta xk added up for k equals 1 to n, but each of these little mk's is 0. So I get that my upper Darboux sum is 1 and my lower Darboux sum is 0. And one of the things I want you to notice here is that I never used any facts about this particular partition I chose other than that it's a partition of the interval 0, 1. I used nothing about the actual values of this partition here. So it actually turns out here that if you take any partition of 0, 1, the upper Darboux sum will be 1. And if you take any partition of 0, 1, the lower Darboux sum of the function will be 0. Okay, so these are really more properties of this function on the interval than having anything to do with the particular partition here. Now, of course, for other functions, this isn't necessarily the case. Your upper and lower Darboux sums for some other functions will change as you change that partition. But in this particular case, for this function, the upper and lower Darboux sums are independent of the actual partition values you choose, just the fact that it's a partition of 0, 1. So where we're going to go from here is we are going to next work to define a couple of different things. So we will define what it means for a function to be Riemann integrable. We will define things called upper and lower Riemann integrals. And we will see that those have a relationship to the Riemann integral itself. And we will often make use of these upper and lower Darboux sums to help us prove things related to that. So moving forward in the next video, we will look at the definition of Riemann integrability and a couple of sort of equivalent conditions to being Riemann integrable. And then we'll begin pushing forward, trying to prove common facts that you encounter about the Riemann integral in a calculus course. For example, proving that the integral of a sum of two functions is equal to the sum of the integrals of each respective function. So that will be our goal moving forward. Again, in the next video, we will look at a formal definition of Riemann integrability.